In this lesson, I'm going to be showing you how to solve differential equation by integrating factor. And this method right here is very important because we are going to need the process here when learning how to solve linear differential equation, especially the non-homogeneous. So I want you to pay attention to this process from beginning to the end because they are going to prove very useful. So let's get right into it. But before we go into integrating factor, I hope you probably are aware of the method for solving an exact differential equation. A differential equation of the form m dx plus n dy equal 0 can be an exact differential equation. So when a differential equation is in this form, you carry out the test for exactness, and the condition for exactness of a differential equation like this is if the partial derivative of m with respect to y is equal to the partial derivative of the n right here to x. So if this holds true, then you know this differential equation is exact. Then to go on and solve this, what do? So you set a function u of s comma y that is going to be the original function that yields this differential equation, and it's going to be equal to the integral of m dx and plus some function k of y equal to c. So how do you obtain this function k of y? To obtain the function k of y right here, so take the derivative of u with respect to y. When you take the derivative of u with respect to y, you obtain some function here, so and plus the derivative of k with respect to y. Now at this point, what you should do is write out the function n here. Put it down right here, side by side with the derivative of u you just take, and that is going to give you some function which is the same as what you have right here, and probably some other function of y. Okay, so what you will do at this point is simply equate this to equate the k, the y, with the function y obtained, and you know this is a simple differential equation that can be separated. So you separate this and you obtain the k equals f of y dy. When you integrate both sides, you obtain k is equal to the integral of f of y dy. And this right here is what you're going to put back here, and you would have solved this exact differential equation. So I just thought it might be cool for me to explain this first before jumping into this, because this is essential. Now let's move on. And so how do you obtain the integrating factor for a differential equation? So let me go on and wipe what we have here, because we're going to need some space for this. So we are not actually solving a specific problem in this case instead. So we are going to be looking through the process, the method for solving a differential equation, making use of the integrating factor. And we are going to need this when a differential equation is not exact. So let's go through the process that we just went through now. Let's go through it once again. So when we have a differential equation, m dx and plus n dy equals 0, like we just did. So when you carry out the test for exactness, you test for partial n, partial y, and you find that is not equal to partial n, partial x. In that case, there is some function of x or some function of y or some function, let's just say some function that can be introduced here that will make this differential equation exact. I know you probably agree with that. So let us call that function f for now, okay? Let the function be f. So let us use that f to multiply all of the equations. So we have f multiplied by m dx plus n dy equal 0. And when we take this product, we have fm dx and plus fn dy equal to 0. So since we know this equation is now exact, because f is a factor that can make this differential equation exact. So since we know this is exact, then that means the partial derivative of f with respect to m, partial derivative of fm with respect to y must be equal to the partial derivative of fn with respect to s. So this holds true. And if we can manage to obtain the function f, then we can put it in here. So now let's go on and do that. Another way of expressing what we have right here, you will notice, is this is a product function, a function fm. You probably recall that when you have a function, say you have a function, let's say when in calculus 3, you learn that when you have a function y equals to uv, you learn that the derivative of y is going to be, you take the derivative of u, you leave v alone, then you leave u alone and take the derivative of v. So, and this is also known as the total differential, right? So it's the product function. So let us rewrite this expression right here in this form. And when we do that, since this and this is what we are taking the derivative, let us leave f alone. So we leave f alone, then let us take the derivative of m with respect to y plus. Next, we are going to take the derivative of f with respect to y, then we leave m alone. This right here will translate the same as what we have here, and that's equal to, next on this side, let's do the same. So this will be, we leave f alone, we'll take the partial derivative of n with respect to x, then plus, we take the partial derivative of f with respect to n, with respect to s, excuse me, and we leave n alone. So at this point, this can be a little bit difficult to deal with, and the reason being that if f is a function of x and y, this can be complicated. So let us assume s is a function of x. Let us assume s is a function of s. So if s actually is a function of s, our problem will be reduced, because if f is a function of x, what would happen to the partial derivative of f with respect to y? Because f is strictly a function of s, then this would be a constant, and that would be 0, right? The partial derivative of a constant is 0, right? So, and 0 multiplied by m, that means this term right here would be out of the whole thing, and it will be left with f multiplied by the partial derivative of m with respect to y. Now this right here is can equals f multiplied by the partial derivative of n with respect to x, right? And plus, next we have n and multiplied by the partial derivative of f with respect to x. Okay? So at this point, what you should do is, let us multiply everything right here by 1 divided by fn. Okay? We have n and f here. So when we do that, this will be reduced to 1 divided by n partial m partial y. And this will be reduced to 1 over n as well, right? And partial n partial x. And this will be reduced to 1 over f partial x. So when we bring this right here on this side, because we have 1 over n all over the place there, so we have 1 divided by n partial m partial y minus 1 over n partial, and I'm wasting time on this. I assume you already know how to do this already. So 1 over f partial x. So we factor 1 over n out of this, and we have partial n partial y minus partial n partial x equals 1 over f partial x. At this point, you will notice that our problem is almost solved completely, because if we set everything here equals something, like let us set everything is equal to something, all of this, let it be something like, say, r, okay? So you know we have 1 over f partial x is equal to r. Now, since we are certain that f is a function of x, we can say this is the f dx, because we have chosen that f is a function of x. So, and you know, to solve this, we can separate the variable here. We multiply both sides by dx, and we have 1 over f df equals r dx. Let us integrate both sides. and we have ln, the integral of 1 over f with respect to f is going to be ln of f. And on that side, we have integral of r dx. So to solve this completely, we take the exponent of both sides, right? And we have f equals exponential e to the integral of r ds. And this is the integrating factor. This is the integrating factor that can be employed here to solve this differential equation. Now, you'll notice we have r in here. What is this r? Where this r is everything right here. And that is 1 over n into partial n, partial y, partial n, partial x. I will have to cut that place. I just made a mistake there. Okay, so sorry about that. So, I just made a mistake there. I will not lie to you. So, this is partial m, partial y. So, I'm supposed to put down partial m here. Okay, you should notice that I'm supposed to put down partial m there. So, n minus partial n, partial x. That is r. So, therefore, when we have a differential equation of this form, if we obtain this r, we can get a integrating factor that happen to be a function of x. Mind you, this f here, this f right here, is a function of x. Okay, so but the problem is sometimes the function of s may not work. So when the function of s does not satisfy, maybe the function of s is difficult to obtain. So what happened is we look for the function of y. If you go through this process again, assuming taking the function from here, taking the function is a function of y. If you take the function as a function of y, from this point you will notice that the partial derivative of x with respect, partial derivative of x with respect to s, this right here is going to be 0. Because the y we have here is going to be a constant, and this is going to be 0, and this content right here will be gone. And then you can go on and evaluate. So I think I should do that. So what I'm going to do is, let me write this part so that I can put it down there. Going to call that part. Okay. So from here, when we say if the function, if the f here, right, f right here, if it's a function of x, if the f is a function of x, then partial derivative of f with respect to y is going to be a constant. So, and if the partial derivative of f with respect to y is a constant, that was the reason why this component right here got off. Okay. So, but what if the f right here is a function of y? If this right here is a function of y, then the partial derivative of f with respect to s, because this is a function of y, the partial derivative of s with respect to x right here is going to be 0. And for that situation, this component right here is what would be out of the equation here. So we can rewrite this property then. So we are going to be having f multiplied by partial m, partial y, plus partial f, partial y multiplied by m equals f partial n, partial x. I hope you understand this. You can pause this video and go through the process properly, so that you don't miss anything. So at this point, let us repeat what we did the other time. Remember? So at this point, we divide both sides this time by fm. And we divide both sides by fm in this case. Dividing this by fm, this reduced to 1 over m. And you have partial m, partial y. Dividing this by 1 over fm, this is reduced to 1 over f. And you have partial f, partial y. And this reduced into 1 over m partial n partial x. So when we take this component right here to the other side, we have 1 over f partial y equals 1 over m partial n partial x minus 1 over m partial y. I hope you get this. So we are repeating the process we went through the other time to obtain the r the other time, right? So we have, if we factor 1 over m out of this, we have partial n over partial x minus partial m partial y. Now this right here, don't let us call it r again. This time let us call it something else, because this time we should not give it the same name as what we give to the other property. So let's give this r star, okay, where this is 1 over f, and this f right here is a function of y. So we have partial f partial y. So you can see our problem is reduced again. We can simply equate this part, this 1 and 3. 1 over f partial y equals r star. We don't want to give it the same name as the other. That's why I'm putting star here. So, and to solve this completely, we separate the variable. We have 1 over f partial f equals r star partial y. We integrate both sides, right? And we have ln of f equals integral of r star partial y. And then we take the exponent of both sides, and we have the function of y this time. Remember, the other integrating factor was a function of x. So, and this will be equal to the integral of r star partial y. So I don't have to say partial y, so I can say dy, because, and the reason for that is because I am sure that this is strictly a function of y, and everything right here is a strictly function of y. Now, excuse me, I did not put the exponential there. So look at that there. What is r? What is the r star that we have there? The r star is 1 all over the component right here. 1 all over m into partial n partial x minus partial m partial y. So, and this integrating factor can help us to solve this differential equation. Now, we are going to need this knowledge right here when we are learning how to solve a linear differential equation, because all these different types of differential equation most of the time are just different ways of expressing the same thing, but they are different in property, and we could use the advantage of the knowledge we had when solving one of them when we are solving another. So do not forget this part right here. So what I'm going to do is, so that you'll be prepared for the next content, next part of this video, I'm going to I want to write this part here. The takeaway right here in preparation for the next lesson is this component, this part right here. So when you have 1 over f partial x is equal to 1 all over n into partial m partial y and minus partial n partial x. And we said this is equal to r. So also in this part we have 1 over f partial y equals 1 all over m into partial n partial x minus partial m partial y. And this is what we call r star. And we are going to make use of this when we are solving, when we are studying how to solve non-homogeneous linear differential equation. So, and that's it. Please, I'm going to put a link to a description on some example of problem I've solved in the past on this channel, just in case if you want to see the other methods that I've used to solve the same problem. It's similar approach, but it's slightly different, okay? So, and that's it. See you in the next one.